So just to say, I'll be back for lunch. I'll wait a few minutes. I'll wait till 5 past to start. We're quite a relaxed schedule for this afternoon, and then I'll start. So yes, if you've got a graph, that'll be great. I'll just do a screen share once we start the session, and then we can just see it on your. So the main point is that we'll see that MPI-IO has what they call aggregate. MPI nominates a subset of the processes to be the IO processes. What it does is it tries to match the number of IO processes to the number of stripes. So the idea is that if there are 4 stripes, MPI-IO will try and nominate 4 IO processes to write to those stripes so that there's this match. The problem is that, as we saw, a single process can nowhere near saturate an OST. But that's why you do get so in terms of qualitatively, these graphs make sense because for unstriped, there's not really much benefit in increasing the number of nodes because, as you said, you're just writing to a single. You're writing to a single. What do I call it? A single OST. If you double the number of stripes, okay, then you get almost twice the bandwidth. But it doesn't. There's no. But you're limited by effectively the number of stripes. The best thing is when you have lots of stripes and lots of nodes. So that's why the striped ones are about double the unstriped. Sorry, yeah, and the full striped carry on. Now you do get some contention, but you can see up to at least 4. It's linear up to 4 stripes, which is nice. If up to 4 stripes is almost linear, then we get some contention, but it still increases. So qualitatively, those graphs look really nice. You can sort of understand them that you don't get any parallel I/O when you have unstriped files, and if you have striped files, you get parallel I/O up to a maximum of effectively the number of stripes. The problem is that the actual absolute performance is disappointing. It's a maximum of 4 or 5 gigabytes per second. I mean, for the disk file system, that's under 10% of the maximum, but for the NVMe, it's about 1%. So that really looks quite bad. And the reason is that, as I said, that's a really nice graph, actually. That's really excellent data. The reason is that this idea of matching having the same number of I/O processes as stripes assumes that a single I/O process can saturate a stripe, and we've seen that we're an order of magnitude away from that, a factor of 20 away from that, I think, wasn't we? So that's the problem. So there are, but we'll see how to check. We'll see how to try and change that. Now it doesn't work as well as you might hope. For reasons we don't quite understand. I think there's something which we're calling with HPE. But anyway, I think I understand that that graph. That's really nice data, actually. So the thing which really doesn't make sense there is that NVMe is slower. You wouldn't expect NVMe to be a lot faster because you're limited by the I/O from a single process, not by the raw speed of the disk. But you would not expect it to be slower. No, I think the opposite. I think the NVMe is not that heavily used. I mean, that's why, there aren't, it isn't that heavily used. For example, if I share my screen, well, at least in terms of, if I share my screen here. Where's Eleanor? Oh, the wrong one. So if I'm in the, that's just my, if I ls, you'll see that on r/work disk, actually maybe not, well, where are we? We're on work 2. Okay, there's a soft link, but if we, if we let, this is where we are. Okay, that there are 143 projects. So each of these directories is a project. 143. So I mean, I presume that that's a lot of users. But 143 projects are on work too. But if we look at the other one, which is AFS2 NVMe/work, there are 13. So unless these guys are massively hammering it, I don't think they are. Again, it could be the, I don't know actually. I haven't. That's really nice. Could you, Louis? Could you email me that Excel sheet? Yeah, no, it doesn't make a lot of sense. Yeah, that would be really good if you could. That's very interesting. We have a nightly run of bench IO to try and monitor the bandwidth, but it's really been we've not looked at scalability. It's really because there were times when the IO system was crawling and we needed to pick that up. But that's nice clean data. But I said qualitatively it looks great. It's just quantitatively you'd hope the multiplier to be bigger. But that'd be really good. Okay, excellent. So that was that. Hope you enjoyed that. So now I'm going to go to the next lecture, which is talking about SVN. Just talking about how we can configure Lustre to try and be better. And then the next exercise will be maybe playing around a bit with the where are we? So a lecture. Oh, I probably have it open already, don't I? Yeah, sorry, I should have just. So it's just a short, really, just a couple of short talks after lunch and a I'm having to set up the show, the slideshow. Okay, fine. So if I share this window, then we can get going. Sorry about this. I'm getting there's some slight funniness going on with my it was not wanting to share the correct window. I'll try again. Don't know why it's doing that. It wasn't showing up. There it is. Okay, it wasn't showing me the window I wanted to share. Sorry about that. So, we've already seen that clearly striping is essential to getting good performance. But what are the general hints for configuring efficient use of Lustre? So, the question is, what are the bottlenecks? And I think, we've seen from these benchmarks that it's clear that the bottleneck aren't the OSTs on 16 nodes and 12 stripes. You're looking at potentially over 100 gigabytes per second. We're getting single digits, and so actually and it didn't seem to be that it wasn't the network, because we're able to chuck out 15 gigabytes a second from a node. So it seems very much with the current configuration that the bottleneck is the fact that the I/O speed from a single process is low. Okay, so of course, I've given this a bit before, but of course, I/O eventually is very difficult to be non-reproducible. You're sharing ARCHER2 with other users. Someone else may be writing the same OST. Someone else may be using the same network links. Actually, also caching can give very high I/O rates because data can be cached in local memory. Okay. But also these OSSs may cache, and they may be caching on the OSTs as well, because these are all servers, basically fully configured servers. So it can be quite difficult to get, it can be quite difficult to understand rates. And that's actually more true of read. Reading can be a real problem. So the main thing is ensure benchmarks are for a reasonable time, like a few seconds, and that requires large amounts of data. And you want to repeat them several times. And that's what, I mean, Luca, who's helping out today, has set up a bunch of regular tests which do that. So the ARCHER2 hardware, we've seen this before, but just to recap, there are 3 separate /work file systems. We've got 12 OSTs and 1 MDS. And we're on work, were we on work 2? And this additional file system with solid state disks, not the spinning disks. I said still to be configured. That's not completely true. Since this talk was written, you now have access on request. And each has a RAM. We've seen this before. So serial I/O, you're not using parallel. So if you're not using parallel libraries, then there's, which could be single file with controller I/O or file per process, there's little point in striping the file. And the reasons are, for a single file, the performance bottlenecks are elsewhere. As we said, for a single file, if you're just writing one file with a controller I/O, clearly the bottleneck is like less than a gigabyte per second from the controller process. But more importantly, and someone pointed this out, which was very nice, with multiple files, you're already parallel. You're using many disks. So if you're not using a parallel library to do your I/O, there's little point in striping the file, which is why single stripe is the default. And I've got a ballpark figure. Single process can achieve up 1 gigabyte per second. And that is something we've seen. It's a bit less than that now. Again, it could be contention on the file system. Don't really understand. So the MDS can become overloaded. So every time you open and close a file requires access. So basically, imagine I'm going to do parallel I/O to all these disks. At the stage I'm doing I/O, it's completely in parallel. Imagine each of these nodes has got an I/O process on it. They can each write to each of the OSTs in parallel. However, to work out what to do, maybe to open a file or to inquire where all the different stripes and things live, requires access to the MDS, which is a serial bottleneck. And if you imagine, so that can easily become a bottleneck. Now, it's not so bad as it used to be on the previous system, Archer. It was really slow. The classic things you do now is that for the metadata server, its storage target is maybe a solid state disk. So I think even on the work file systems, which have the standard work file systems, which have spinning disk, old-fashioned disk for the OSTs, I think the MDS itself is stored on an SSD, so it can do lots of really quick lookups for the metadata. But opening and closing a file requires MDS access. This is therefore a serial operation, and you share the MDS with all users on the same file system. So one of the classic issues we see is that people have they're writing a log file, and they have, whenever they write to the log file, they open, seek to the end, write and close. That is a total disaster because you're doing an MDS lookup for every single I/O operation. So you should not do multiple open, seek, close operations on the same file. I think there's a package called OpenFOAM, which is an engineering fluid dynamics package, which by default does this, and it's just a disaster for performance. Because as I was saying, the whole Lustre file system is and all parallel file systems are optimized for bandwidth at the expense of latency. So a lot of the startup costs, database lookup costs can be high, and the MDS can become overloaded very quickly. Even if you're not sharing the MDS, try not to write too many files. If you write a file per process, we had this a while back with a user who was writing. They were running on 256 nodes, and so they were 256 times. They were opening 30,000 files. They were doing file per process, and they were opening 30,000 files. The whole file system just ground to a halt. And a trick there, try not to write too many files. A simple trick there is a file per mode rather than a file per process. That you can base, and that's why I've included that as an option in the bench IO. You simply on a node, you basically take it in turns to write the file. So each client, remember, each node is a client of the Lustre file system. That means that there's only, each client is only doing one IO operation at once. So that is a very simple trick, just to bring, and that brings down the number of files on ARCHER2 by a factor of 128. There was a question there, sorry, as ever, I have got lost in all these windows. Okay, I found it. Yes, you told me, Vanessa. That's fine. I am recording, Vanessa. Yes, that's fine. Yeah. So if you must have lots of files, consider multiple directories, because looking up a file in a directory is a serial operation. You have to scan through all the files, and if you have multiple directories, then that just reduces that overhead. So, for example, another thing you might do is a directory per node. So, if you must have lots of files, try storing them in a different directory for each node, and that will at least ease things a bit. It decreases the lookup time for files. But really, this is saying that at very large scale, the tens of thousands of processes, file per process really doesn't work. The stripe size, the default is 1 megabyte. It seems quite small for large data. If you're writing gigabytes, then a megabyte seems quite small. You can experiment with larger settings. Now don't set it too large. If you set it too large, you won't be using all the OSTs, because if you have gigabyte files and you have a stripe size of 200 megabytes, then you can't. Then you're not going to be using more than you're not going to be using all. You're only going to be using 5 of the OSTs, no matter what your striping is. Having said that, I have found a megabyte to be surprisingly, although it sounds quite small, to be surprisingly good. I haven't seen much benefit in increasing that. So, but really, how does parallel I/O work, and why are we getting this reasonably good scaling for MPI-IO, but the actual base I/O speed is not brilliant? Well, MPI-IO auto-configures to the Lustre settings. So what it does is it identifies a small number of aggregator processes. So it says, I will identify a small number, say 10 processes, who will gather all the data from the other processes. Now, this is hidden to you beneath the hood, but MPI-IO will identify a number of aggregator processes, and it will try and spread them across nodes. Because remember, you want to have I/O from different nodes, because different nodes have different network connections and are separate clients of the system. Then use collectives, scatter or gather, depending whether you're doing read or write, to aggregate it to these processes. And then that allows you to perform a small number of large write operations. You bring in the data to a smaller number of processes, and then you write. You rearrange the data into nice contiguous blocks, and then you write. And that minimizes the overhead of locking, etc., because you're basically you're not interleaving lots of different I/O requests. You've sorted the data in a way which means you can do a small number of large writes. This is only possible with collective I/O calls. If you don't call a collective I/O call, then MPI cannot aggregate the data because it does not know that the other processes are taking part. It's only with a collective call, MPI-IO or any of your I/O libraries know everyone is taking part, so that I can gather all the data and do this trick. And it increases the I/O orders of magnitude. So Louis says, is the number of aggregator processes tied to the number of available memory for each process, or can it run into problems? So it will. When I say gathered all the data, I presume it will have some. It will work out how much free memory it has and gather it in chunks of that size. So I think I've not seen a problem. No, the number of aggregator processes doesn't vary with the memory, at least on the Cray implementation. But what it will do is it will probably just grab all the available memory. It will gather the data in chunks. I've been a bit naive here saying gathering all the data. It won't gather all the data. It will gather as much data as it can. Does that make sense? Yeah. So maybe yeah. Okay. You can get useful runtime statistics. The MPI-CH MPI-IO stats equals 1. If you put that in your Slurm script, what that does is it prints out information on how many actual file system read and writes did I do. And if you do a lot of collective I/O, then that will be a small number. You'll see I did a small number of system writes, each of which had a big write size. But if you have, say, doing a large number of writes, each with this, then you're not doing collective I/O very well. And this doesn't just work for MPI-IO, it works for any library that calls MPI-IO. So for HDF5, which we'll see is layered on top, you also get useful stats. So if you want to, if you have a simple question of, is my I/O pattern benefiting from data aggregation, you can set this environment variable and you'll get a short text report at the end of your run saying what happened, and that can be quite useful. So what would happen, again, modulo memory limits, is a 4x4 array on a 2x2 process grid, okay? Imagine we had, it doesn't, what we would want is we'd want, if we had 4 stripes, we'd identify 4 aggregator processes. And so each aggregator process would aggregate the data for each disk. So what we're saying is that we have 4 stripes here, which are on disk 1, disk 2, disk 3, disk 4, OST1, OST2, OST4. We have a separate aggregator. Well, in fact, here we have the same, not everyone's an aggregator process, but we'd have a separate aggregator process for each stripe, for each disk. And this guy would say, well, I need to collect this data here. And having collected it, I can write that as a single block. And the important point is not only does it do a single write, because you know you have 1 aggregator process per OST, you know there can be no, you don't need to lock this at all, because you know that you're the only person writing that OST. And that's why the default is 1 aggregator per stripe, 1 aggregator per OST. That means that you only ever have 1 process writing the OST, so you don't need to bother about file lock, you don't need to bother about file locking or anything like that. So this is the way it would work. Each would then do only each disk would actually have only a single, you'd see 1 very large I/O operation being done to this disk. So that's the way the aggregation works. Again, it's a very simple example, but it generalizes to much more complicated situations. So the aggregator processes are MPI processes. So these are actually MPI processes. One of your MPI processes will, inside the library, will say, okay, I'm going to, those are actually your, these are actually your MPI processes. When you call the library, if there were, your MPI process, say you have 10 MPI process, sorry, 100 MPI processes, and you've got 10 aggregators, then rank 10 would say, like, I'm the boss guy of ranks 10 to 19 inclusive, and it would do a gather of all the data from ranks 10 to 19 onto it itself and then write. Does that make sense? So the aggregator processes really are your MPI processes, but they're running that's within the library. That makes sense. But so they run on the compute nodes. Sorry. Now there will be, so I don't know what happens. That's a very good point. Okay, so I should show the diagram again. Actually, that's I've never not explained this very well. That's a very good question. Yes, for this 2x2 example, but what happens is, yes, so a subset of these processes will write. They will gather. Then when they do the write, the data will flow through the network to the OS. And there's clearly other stuff going on here. I mean, who knows what's going on in the library? There'll be other processes coping with it. But from these aggregator processes are on the compute nodes. That's what I mean by an aggregator process. It's a subset of the MPI processes take a different role. So by default, Cray MPI uses 1 aggregator per stripe. It sounds good, but this does not see as a single process I/O is slow. And this is 1 aggregator per stripe is my example of well, this is my example here was having only 1 carriage door open per railway carriage. You just can't get the data out of that out of the node quick enough. So that sounds, so this default could be changed. So to use 4 times as many aggregators, say 4 per node, you have this really, yes, this because this is a trivial example. Yes, you're right. You're right that yes, you're right. Yeah, I maybe need to use a bigger. It's difficult because it's hard to draw bigger examples than. I probably need a 4x4. I probably need a 16x16 example to show that. Well, no, actually, okay. So this does show something. The point is, I want this is how I want the data to lay out in the thing in the file. Is how I want the data to be laid out. Okay, I want it to be laid out. Okay, it's more complicated than that. This is assuming that we have one stripe. This is really just a kind of this is assuming we have one stripe per disk. That this is the stripe size is the same as the size on disk. So yeah, maybe I would need. I mean, it gets. Yeah. That is okay. So that is identifying the data that goes onto each disk actually requires you to know the stripe size as well as the data layout. So it's actually more complicated than that. But you can still illustrate it in this simple case if you assume the stripe size is the same as the amount on each disk. Yeah, I maybe need to work on that example, but yeah. So you can increase the number of aggregators. So this is opening more doors on each railway carriage. And this is very, very strange syntax, which says X for MPI, MPI equals Cray CB nodes multiplier equals 4. Don't really know, but that says use 4 times as many aggregators as you thought. And the star here means you do it on every file. Okay. However, the problem when you have more aggregators than that's actually wrong. So apologies. This is when it's 4 per stripe. Sorry about that. It's 4 per stripe. Sorry, I'll update that. The problem when you have multiple aggregators is you have more than one process writing to each stripe. You have more than one process writing to each disk, and that means they tend to lock each other out because they're worried about writing to the same file. So there's this other bizarre. But HPE told us that the default locking approach, which is to completely lock the file, is very inefficient. There's a more efficient locking mode which only locks, I think, per stripe, not per OST. And that's Cray CB write lock mode equals 2. So this is the magic incantation to try and get better bandwidth. It says use more aggregators than the default, and trust me, they're not going to interfere with each other. It's okay. You can use a more relaxed locking approach. So that I have a couple of papers which I'm just about to upload to which go through this, give some results. But at the moment, they're just kind of magic incantations. Another thing we noticed is that these aggregators use MPI collectives. So each of the denominated aggregators will use an MPI collective to gather all the data it needs to write. It turns out that by default, those MPI collectives can be rather slow. And there are actually 2 versions of MPI on ARCHER2. One uses, and this is the very lowest level. What's the lowest level protocol used to transfer data over the network? The default is OFI, Open Fabrics Interface, and it can have very poor performance. There is this magic environment setting. It's all rather unsatisfactory, these magic settings, but this is what we've been advised to do. That this increases the collective. Without this, your multi-node parallel MPI-IO performance is very poor. However, there is an alternative low-level interface written by Mellanox called UCX, and this actually, this should improve the results. And you don't need to recompile. You just do this in your script. You just tell the MPI not to use OFI but to use UCX. You have to change the network layer and change the version of MPI. But I think if you rerun your results like that, I think you will see significantly better performance, or at least significantly better scalability. That's in the exercises. And common mistakes people make, just as a general comment. Sierra, text data files are spectacularly slow. They're bloated because if you write a number out in so Luca's saying it does locking. And so, yeah. So, yeah, text data files, they're bloated. It's a lot more data to store a double precision floating point number in text than binary. Also, you have to do a conversion to and from binary. It's incredibly slow. That's a real con. Don't do text data files for big I/O. Multiple accesses to a large number of small files. That's a real problem. That increases the metadata load. And the other one is using striping for serial I/O. That will not benefit it. And as we saw, if you're doing lots of serial writes, lots of file per process, striping can actually hinder the performance. Parallel I/O mistakes. We often see people say, okay, I've just gone away and spent a month implementing MPI-IO into my code, but the I/O doesn't go any faster. There's no point using a parallel I/O library unless you stripe the file. So I would recommend full striping across all the OSTs. I've rarely seen a situation where striping across. So my bottom line is either no striping, i.e. one stripe, or full striping. Using non-collective, i.e. individual I/O to a single file, you have to call collective I/O, and that allows all these tricks, such as data aggregation, which have an incredibly beneficial effect on performance. The other one is, people come along and they say, my I/O performance is poor. What do you mean? It takes half an hour. I mean, you need to quantify it. It's like someone coming to me and saying, my commute to work is long. How long does it take you? Half an hour. Well, I don't know if that's good or bad. If you're traveling 50 kilometers between Edinburgh and Glasgow, that sounds quite good. If you work 100 yards from where you live, that half an hour is bad. So you have to quantify the performance in gigabytes per second to get any, because often the reason that people's I/O takes a long time is simply because they have huge amounts of data. This is slightly, you should be achieving an excess of 10 gigabytes per second per parallel write. The numbers we're getting today are slightly less than that. I think because the ARCHER2 is so much more busy than it was 2 years ago when I did my initial benchmarking. I'd be interested to know what Luis's nice graph looks like with the UCX library, maybe even just for the 16 node numbers. Switching to UCX had very beneficial effect before. So, but I think the main thing is if you're worried about your I/O performance, don't just say it takes a long time. Quantify the performance in terms of gigabytes per second, and then you'll get some idea. And that's why Bench I/O is useful, though it's a very, very simple program. It gives you some feeling for what you should be able to get. So if UCX is so much, so it's not better for everything. So the problem is, it's a very good question. UCX is better. We see that UCX seems to be better for collective operations for very large collective operations which are shoveling around gigabytes of data. It's actually slower for point-to-point communication. The latency of send and receive is slower in UCX. So if your code is a multi-dimensional like halo swapping code, sending and receiving boundary data, or your code is sending a large number of small messages, then it will be slower. So also, UCX is only there by happenstance. It's a long story, but UCX is not available on the HPE. These HPE systems were targeted at OFI. The fact that UCX is available is something of a quirk of history. So on a more modern, if you bought a similar machine to ARCHER2 today, you'd have a more modern version of the network. You'd have something called Slingshot 11. We have Slingshot 10, and UCX would not be an option. So I think those are the two reasons why it's not the default. It's not really supported by HPE, but it happens to be available. But also for point-to-point communication, it's actually slightly slower. And also, it's a global change. It would be nice to say use UCX for my I/O, use OFI for my point-to-point, but you can't do that. It's a one-off. Your program runs using one or the other protocol. That's a good one. concludes for parallel I/O to single shared file, use a high-level parallel I/O library, use collective calls, and there's going to be one caveat to this. You'll see the final line. In general, stripe file across all OSTs, LFS stripe -e -1 output. For serial I/O, single or multiple files, do not stripe the files, but consider writing a file per node. Controller I/O, well, you only use single disk anyway, but file per process, file per may overload the MDS. So consider file per node or multiple files per node, but not a file per process. Try a file per 10 or 100 processes. That would be a better thing to do. So that was okay. Just just about on time. The exercise for this is to play around with some of these options. And if I can get the exercise sheet up, which has disappeared as usual. So people have done very nice stuff on MPI-IO performance. Now we can you can look at what these I/O stats are. Try using the alternative version of the Cray MPI library, and as I said, you could try this. You might actually want to try a bigger multiplier than 2. To be honest, we have. I would say that a number like. Okay, I should have a number here from some work which a colleague of mine did. Give me a second, and I'll give you it. So I don't want you to have to spend time needlessly scanning through all the different options. So I think you might as well just head straight for the sweet spot, which I believe I should be able to get this in a second. I'll put these. Yes. Sorry, I need to get the door. I'm really sorry. I've got someone else at the door again. Oh. I'm sorry. I'm busy. I'm doing other calls. Sorry. Sorry, I'm very sorry about the disruption. The advice, which I will put these papers up. So what we found the sweet spot was. You can see that. There we are. Yes. Multiplier equals nodes divided by 4. So that would be multiplier for the biggest one you can do is 16. So multiplier equals 4. Probably that equals 4 is probably better than what I've got in the exercise sheet, which I was saying 2. So this would probably be better to be 4 than 2. And then, okay, so we're going to talk about alternative I/O libraries in the final talk, but there's just a few things we can play around with here, which will be interesting. So this should have an effect, and this would hopefully have an effect. Okay, so what we'll do is we'll just do the exercise. let's say, so yeah, we'll start. So we'll start the exercise about 10 past 3, gives 20 minutes. So the practical on configuring Lustre, which was looking at the UCX versus OFI libraries, possibly varying the multiplier for the number of aggregators per stripe. And I think 4 is probably the sweet spot. And thanks, Luca, for that. I'll put up those papers as well. And the final talk is on our other IO libraries, and we expect to finish shortly after. I'm happy to be back at 4 to help you. Just in case, just to look ahead, there is the most modern IO library we have, which is the one I know kind of least about, but other people know more than me. It's something called ARCHER2, and that at the moment seems to get the best IO performance, and I think we understand why, and I'll explain why. Because ARCHER2 takes a different approach under the hood to a different approach to data aggregation than MPI-IO, HDF5 and NetCDF. But that'll be the exercise for now. And also, so I'll be around. I'll take a quick break, but I'll be around till 10 past to help you with the practical, and then I'll give a talk at 10 past 3. Expect to finish shortly after 3:30. I realized why that is. So I know. Okay, so I know why. So sorry, the last time I ran this course, we didn't have the ADIOS library, and that wasn't an error. But now we have the ADIOS library, and yeah. So what you need to do, apologies, my mistake, is you need to you need to oh, that's not very good, is it? That's not very good. Okay, is that UCX? Okay, so oh no, it can't be UCX. So in your Aaron, in the well, sorry. So so Luis, you're able to use UCX. A strength that no, you don't. I don't under, I've seen this error before, but it's sort of intermittent, which is why I'm surprised. Yeah, why I'm surprised that Aaron's getting it and Louis isn't, which is weird. That is strange. Yeah, I think you may have to do. Why is this? I think you probably have to do module load lib fabric. Does that work, Aaron? So there's a more elegant fix than that. Or apologies. I reran these scripts, but I didn't rerun them with. I reran them to check Adios 2 work. I didn't check it worked with that. Okay, yeah, it's a quirk. It's a quirk. Right, fine. Thanks. Yeah, it's a quirk. Sorry, I didn't check that out before. So Luis is asking about that. So that weird export, basically what it does is there's some internal buffer size which is used by OFI. So the OFI library will do different things for messages below or above 64 kilobytes, and for some reason, sorry, I don't. Some reason for it's to do with some internal buffer size. So for some reason, that if you set that limit to be 64K, then it helps for large collectives. I'm not sure what the default is. I should know, but I don't know what the default is. Let's have a look. So the default is bigger than that. Okay. So if you, it's a so messages. Okay, so it's basically saying so at the lowest level, by default, messages below 256 kilobytes, because the default is no, there was a default. Sorry, I forgot the default. So the default's 256K. So really, I don't know, but basically, there's a trick whereby messages below a certain limit are split into multiple smaller messages and then sent, and it's making that threshold smaller. So for some reason, for large collectives, segmentation and reassembly is not advantageous. I mean that we never got a. It changes the way that messages are sent at the lowest level, but why that benefits collectives is beyond. I don't understand. Yeah, it's magic. Yeah, don't understand why. Okay, so I didn't know if anyone had. Did anyone get better values with UCX? So I think Louise said that you. So apologies. I need to fix the script so it worked with UCX. But did anyone? I mean, it looked like for non-UCX, the best that we were getting. I mean, Louise sent me his nice graph. The best we were getting was like 5 or 6, 4 or 5 gigabytes per second. I don't know if anyone got any faster than that with the beta. I could run it, but I have put up a couple of papers, which again, these results are out of date, and in fact, these results are possibly better than we see now for reasons which I don't really understand. It's something we're following up with HPE at the moment, but oh yeah, so if I've put up a couple of papers which I can point you at. So just on the main page here, I reload. I probably have to reload. This is hopefully the page you've been looking at, and at the bottom here, I put down a couple of papers. This is something I did a year or so ago. That looks very glamorous, Monterey, California, but I got COVID a week before, so I never went. I did it remotely. And this is so I said the important point is this is before we knew about this weird locking mode, and this is after. That's to explain why there's two reports with slightly contradictory results. But if we look at this report here, UCX, how many nodes was that? Is that 16 nodes? Just interesting. 8 nodes. Okay, so that's interesting because I have a. Let's have a look. If I basically, so I don't have time to go through this paper, but this was a year and a half ago when things did seem to. I think the machine was much less loaded then, but I was getting. Yes, that's similar to So when I was doing it this time, oh no, that's not the right MPI-IO. Okay, for UCX. MPI-IO to single shared file using UCX on 8 nodes with full striping. I was getting slightly above I was getting about 6 or 7, and that you said 5 or 6. Yeah, okay. So it was a bit. It seemed to go down, but there seems to be about a 10% drop. But you can see that if I do MPI to a single shared file using UCX, if I fully stripe the file, then I get linear increasing, pretty not linear, but I get increasing IO speeds all the way up to about 8 to 10 gigabytes per second on 16 nodes using UCX. For OFI, it tailed off at sort of 4 or 5, which is kind of what we're seeing here. So, yeah. However, we didn't know about this lock mode equals 2, and when we discovered that, we went back and redid the study, and that is this the second report, which I don't have time to go through here, but the second report is this a technical report for EuroCC, which is done mainly by my colleague Stephen Farr. So. Okay, so I don't want to keep you. I'm going to go slightly over the time, but this is the last lecture, and I'll be around. So apologies for slightly overrunning, but it has been very useful. If I now get the final lecture, which is really just going quite a short lecture to talk about the different IO libraries that are available, and in particular. I have to. Apologies for these delays. There's quite a lot of messing around to get PowerPoint to work in a way which is useful. Okay, so we should have. Okay, so this is quite a short talk, but I'll talk about alternative parallel IO libraries, not MPI-IO. So I'll talk about what the issues with MPI-IO are, and I'll talk about HDF5, NetCDF, ARCHER2, and then a summary. And there's an exercise which you're welcome to try. So issues with MPI-IO, the files are just raw bytes. If you look at an MPI-IO file, it's exactly the same size as you would expect if you do a native format. The important part, there's no header information. So if I was doing a climate simulation or an electrodynamic simulation and produced an MPI-IO file, I hand it to my colleague, and it's very difficult to deal with in other codes downstream, because if you want to do pre or post processing or visualization, there's no metadata, it's just bytes, but it can be very fast. So what we want to get the speed of MPI-IO, but we want to have a more standard format, which is portable. And so the solution is that we define higher level formats which have metadata. So if we wrote a 10 gigabyte file, it wouldn't be 10 gigabytes long, there'd be a few kilobytes of metadata at the front. And so, for example, it would know that it's a 4x5x7 array of doubles. And that means that downstream, you can have standard data converters, browsers, viewers, etc. like that. So for visualization and post-processing, it's much more useful. So that's for functionality. But if I'm writing one of these libraries, I don't want to go away and reinvent the wheel. So what you want to do is, for performance, you want to use MPI-IO for the main bulk of writing the data to file. So that's what they do. Many real applications use higher level formats. HDF5 is the most common, but NetCDF I've also heard about in the climate community. But basically, they write some header data, but they write the bulk of the data using MPI-IO if you use the parallel version. So your understanding of MPI-IO will translate the things about when to stripe and how to stripe and such like, and data aggregation, all translate to these higher level formats. So I'm going to very briefly go through them. HDF5 is a very general format, hierarchical data format 5. This is from Wikipedia. It's a set of file formats designed to store and organize large amounts of data. If you use the parallel version, and you'll see it's on ARCHER2, it's Cray HDF5 parallel, then it will use MPI-IO for the bulk of the data writing, and therefore you the normal rules apply. Stripe the file because it's parallel IO to a single file, and use collective IO. And I mean, as I said, the key stage in any parallel IO library is defining how the local data on each process maps to the global data. What's the mapping from local to global data? And we saw that, mentioned briefly for MPI-IO, that was done using derived data types. In HDF5, it has something called hyperslabs. So hyperslabs are basically n-dimensional subsets of n-dimensional data. And so in HDF5, I've just used Fortran here because that's. But what you do in HDF5 to define each process calls this to say which subset of the global data set. It calls something called H5 select hyperslab, where this file space encodes the global size of the file. This says I'm using Fortran. The offsets are where the data starts, and the counts are the subsizes. So you're basically specifying the size and location of an n-dimensional subset of an n-dimensional data set. And then you have to call it a collective write. There's a separate call for collective write. But parallel HDF5 is quite easy to use. If you know HDF5, then using the parallel version is quite straightforward. NetCDF is layered on top of HDF5, so NetCDF calls HDF5, which calls MPI-IO. It's commonly used by climate research, oceanography, and such like. From Wikipedia, set of software libraries and self-describing machine-independent data formats that support the creation, access, and sharing of array-oriented scientific data. So if you basically write a NetCDF file for climate simulation, then you can there are standard viewers for doing graphics and such like, so it's very easy to view. And there's a rich set of tools. And again, you can use, we use NetCDF in Bench.io, but there's a similar thing where basically there is a couple of some random, again, this is from Fortran, but it'll be similar from C or or C. You basically, you open a file identifier, which is NCID. DIMID says, so I'm opening a file, and this is how big the file is. You set a variable to say I want to do collective access, but this put var is the bit where you say, well, this is my starts and subsizes. This is where my data starts, and this is what its size is. This is what subset of the global data I own. So again, it's exactly the same philosophy. as HDF5 and MPI, there are calls which allow you to specify what subset of the global data set each process owns. ARCHER2 is interesting because it's more recent. It can output using native MPI-IO, but it can output in its own format. It can output native and input or HDF5, and its own format is called BP5, binary pack 5. I don't know quite what it is, but the overall philosophy is the same. There are routines where each process defines what portions of the global data it owns, and it calls read-write routines. It's much more configurable than the other format. Almost all the configuration is done at runtime via an XML file. And so there's actually no need to recompile. You can change a lot of things. So if I want to output MPI-IO format or this native BP5 format or HDF5, I don't need to recompile my program. I just change the configuration file. It says here not yet part of MPI-IO, but it is now. So this slide is out of date. But we have seen potential benefit. And the reason is that under the hood, ARCHER2 writes multiple files. Now, I was against multiple files because they're very different. You basically have a data format which is dependent on your process decomposition. However, there is associated metadata. So to you, the user, you don't see that. You just see a single file which you've written, which can be read in a serial program or whatever. But under the hood, ARCHER2 is writing a large number of serial files. So this is why it kind of hopefully gets you the best of both worlds. A data format which is portable, but also which is fast, because it does the quick and dirty thing. Each node just dumps its own data to file. So this comes from bench.io. We have some file identifier. We specify what the global sizes are, where our array starts, and what our subsizes are. This is just the usual thing of saying which portion of the global data set I own. But how is ARCHER2 different? Well, for MPI-IO, HDF5 and NetCDF, the output file is independent of process character decomposition. It writes a single shared file, which is the same as the serial file, which is great, but it means there's a lot of data reorganization and problem with lockings. This BP5 format under the hood writes one file per aggregator. There's no data movement and no locking issues. It basically, for each aggregator, just writes the data. And what it does one aggregator per node. And I haven't written that here, which is poor. But I say that in the sheet. ARCHER2 picks one aggregator per node, and that node just dumps its local data. So there's no data reorganization or whatever, but it writes a metadata file which allows that to be useful later down the line. So actually, the ARCHER2 format is something which I think you should see pretty good performance on, and that would be worth trying to see what kind of performance we get. I haven't tried yet. I only put ARCHER2 into this exercise like at the beginning of the week, so I haven't had a chance to actually do any results. I'll actually run it myself just now. But it's much more flexible, and it is quite a model, and it allows you to do a lot of interesting things. It's a lot more flexible than just writing to file. You can actually interface to other applications through ARCHER2 without ever writing to file. You can do direct, I believe you can do direct application to application data exchange without going via file. So this was just a very, very short talk. The summary is MPI-IO may seem a little low level, but it's the fundamental building block of parallel IO on most systems. A lot of these higher level formats, such as HDF5, layer on top of MPI-IO. So, they don't have to worry about it. They benefit from the performance work done by all the vendors, by Cray or HPE, and by Lustre, etc. HDF5 and NetCDF are common formats that are supported, but you might want to look at the newer ARCHER2 library. But understanding MPI performance is key to getting good performance for HDF5 and NetCDF. And so because I think it's because I believe that under the hood ARCHER2 writes a large number of serial files. Unlike an HDF5 and NetCDF, it may be, and MPI-IO, it may be best not to stripe your files in ARCHER2. But again, this is something I've only just added in, so that's I'm going to check that. So sorry that was a bit of a run through, but I think I wanted to basically say, you should see that the performance of HDF5 and NetCDF are pretty similar to MPI-IO with a slight overhead. The performance characteristics of ARCHER2 may be completely different and maybe a lot better because it doesn't restrict itself to writing a single shared file. It does what seems like the cheap and nasty thing of just dumping the local data per node, but it has supported the metadata to mean that can be disentangled later down the line. So that, as I said, I've finished on time, so I said at 3:30. I hope you found that useful. I am going to put up what next. So I will fix that. Apologies for this error. This is because this is due to having. I'll fix that. I'll fix that and put over a different version. Apologies for that. That's because I've integrated ARCHER2 into BenchIO, but not checked it works with UCX in advance. Apologies about that.